In section 3.6 we're going to be looking at another set of functions that we can take the derivatives of, and specifically we're going to be looking at the trig functions. And your background in trigonometry, you know that there's 6 basic trig functions, and so we're going to be looking at the derivatives of those. This is a screenshot from your book, and you'll definitely want to memorize these 6 basic trig derivatives. We're also going to be looking at the chain rule in terms of derivatives next week, so it's also important to remember that these rules will change a little bit if the argument is anything other than x. So if you notice for each of these, when I'm taking the derivative, the argument never changes. It's x each time. If the argument is anything other than x, I have some other rules that I need to take into account. So again, if the argument's anything other than x, these rules do not apply. And also you need to keep in mind that the value of x that we're looking at has to be measured in radians. So these derivatives only work when we're working in radians, not degrees. Another thing that this kind of the screenshot is showing, there's no parentheses around the arguments of these trig functions, and that's something that I would like you to be doing. So always put parentheses around the arguments of your trig functions, because pretty soon our trig functions are not just going to be this nice little binomial, or sorry, this nice little monomial term. They'll turn into binomial terms, they'll turn into polynomials, they'll turn into product and quotient rules, etc. So it's very important that you always put parentheses around the arguments of your trig functions. And one more time, if the arguments are anything other than x, we need different rules, the chain rule, to be able to work with those. So let's go ahead and look at some examples. The first example we're going to look at is the derivative with respect to x of x squared cosine of x. Now right away we see that this is a product rule. It's a product rule because I have the function x squared times the function cosine of x. The product rule says to take the first function times the derivative of the second function plus the second function times the derivative of the first function. And again, we haven't taken the derivative yet. I've just kind of set up the work here. Now from up above, we know that the derivative of the cosine of x is negative sine of x. And that's from right here. The derivative of cosine of x is negative sine of x. However, I need to multiply these, so you need to remember that without parentheses it looks like I'm subtracting. So we need to make sure we put in some brackets or parentheses or some notation to indicate multiplication. So again, we have the first times the derivative of the second plus the second function times the derivative of the first, and the derivative of x squared is 2x. Now a couple things. Whenever you take the derivative of a trig function, or integrate, which we'll get to in some subsequent chapters, the argument never changes. So we need to make sure that when we write everything here, I want to make sure that I understand that this 2x is not multiplied by this x. So what we usually do is anything that's a coefficient I pull out front. So in this case this negative would be a coefficient, so I'd pull that out front. So before you rewrite anything, make sure that you pull all your coefficients, all your positive and negative signs out front. And the reason this is good to do is you don't get confused with what this argument is. Because it almost might look like you can take x times 2x to get 2x squared here from our argument. But remember, the argument never changes. Whenever you take derivatives of trig functions, the arguments never change. Let's go ahead and look at another example. Let's take the derivative with respect to x. And you don't always have to use x, that's just kind of a common work here. The derivative with respect to x of tangent of x. Now we already know from up above what the derivative with respect to x is. The derivative with respect of tangent of x with respect to x is secant squared of x. So we already know the answer. Let's go ahead and show how that works. Let's kind of prove that. Well, the way that we could prove that is by rewriting tangent. Remember, tangent is equal to sine over cosine. And then right away that you see we have a quotient rule. So the quotient rule starts with the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. Now we have to talk about this squared notation again. With this squared notation, I could write cosine squared to look like cosine squared of x. I could also write it as cosine of x quantity squared. A lot of people are writing it cosine of x squared, and then I also have this other cosine of x squared. So which ones are good? Well, this one is a very obvious notation. I'm squaring the function. This one is a very obvious notation. I'm squaring the function. These other two notations, this one's wrong and this one is ambiguous. So again, this top one is absolutely wrong. I'm squaring the argument. And this one, I'm not sure. Now when we use maple for squaring a trig function, remember I indicated that you should be using this notation right here when we're talking about squaring a trig function. So don't use this notation, it's wrong. This notation is ambiguous, so make sure that if you use it, it's pretty clear what's happening. And again, maple, this is what maple uses. So if you input cosine of x quantity squared over here, maple would output this. Okay, but just be aware that there's some different notations, some you need to avoid because they're incorrect. We have not actually taken the derivative yet. Let's go ahead and look at the derivative here. Cosine of x we just drag along. The derivative of sine of x from up above is cosine of x. From up above, the derivative of cosine of x is negative sine of x. And remember, these are being multiplied together, so you need to make sure that you have your notation indicating that with your brackets. And of course, the denominator hasn't changed, cosine squared of x. Let's go ahead and rewrite this. I have cosine squared of x plus negative times a negative is a positive, sine squared of x all over cosine squared of x. Now at this point, you might be tempted to do some canceling here. For instance, you might say, oh, let's cancel the cosine squareds, but remember you can't. You can only cancel factors, not terms. If you canceled like this, you would be taking this denominator away from the sine squared, and you can't be doing that. So right now I can apply this trig identity. Sine squared plus cosine squared we know equals 1. 1 over cosine squared is secant squared. So this matches exactly with that derivative up here that we thought we'd have. Now you don't ever have to prove this in order to take the derivative of tangent in a problem. It's just one of those derivatives that we memorize. Let's go ahead and look at another example. In this example we're going to be finding the equation of a tangent line. So we're going to find the equation line of the tangent line to the function f of theta equals cosine theta over 1 plus sine theta at the specific point pi over 3. So my function is cosine theta over 1 plus sine theta. I want to find the equation of the tangent line at theta equal pi over 3. Now one thing that we need to be careful about here is not separating this denominator. This does not separate into cosine over 1 plus cosine over sine. Remember, you can never separate the denominator. To write the equation of a tangent line, we need two things. We need a point and a slope. So the point, it looks like we have a good idea already. We already know the value for my x value or my theta value. Now I need my output value, or f of theta. So what I need to do is plug in pi over 3 here to figure out what this other point is. So this other point is f of pi over 3. So let's go ahead and plug in f of pi over 3. That'll give me the cosine of pi over 3 over 1 plus the sine of pi over 3. Okay, we want to simplify this and rewrite. So the cosine of pi over 3 is going to be equal to 1/2. Remember, it's in the first quadrant, so my cosine and sine will be positive. In my denominator, I'm going to have 1 plus the sine of pi over 3. The sine of pi over 3 is going to be equal to the square root of 3 over 2. And then, of course, we're going to want to simplify from here. Find a common denominator. Remember, when you divide by a fraction, you're actually multiplying by the reciprocal, so this flips, cancels. I'm left with 1 over 2 plus root 3. That will be my corresponding y-coordinate. Now usually my y-coordinates are a little bit nicer to work with, but that's what I have for this one. If you wanted to, you could rationalize this denominator as well by multiplying by the conjugate. That'll give us a little bit nicer number to work with here. So I'd be left with 2 minus root 3 in my numerator. My denominator would be 4 plus 2 root 3 minus 2 root 3. And then we're going to have root 3 times root 3, which is 3, and then minus 3. So that's going to be 4 minus 3 is 1. So I'm left with just 2 minus root 3 there. So in order to write the equation of this tangent line, again, we need to know a point and a slope. And the point we figured out from up above. Now the slope is going to be the first derivative evaluated at pi over 3, because the first derivative gives us the slope of the tangent line at any point along the graph. And so the derivative evaluated at pi over 3 would give us the slope of the tangent line at pi over 3. So I think the next thing that we need to look at is determining the value of f prime of theta and then evaluating it. So again, we're trying to figure out what the slope is. The slope is given by f prime of theta, and if you remember from up here, I'm going to have to use the quotient rule. So the quotient rule starts with the bottom function times the derivative of the top function, but this is the derivative with respect to theta. Now we have to be careful here as well. If you don't have these bracketed here, then it's incorrect because that monomial won't get distributed through to the binomial. So again, I have the bottom times the derivative of the top minus the top function times the derivative of the bottom function. And the bottom function is 1 plus sine theta. And this is all over the bottom function squared. So this is going to be over 1 plus sine of theta squared. Now I'm not just squaring the sine of theta, I'm squaring the binomial, so we need to make sure we have those brackets in place. Now we have not taken the derivative, I've just kind of set everything up to show the work on how that derivative will work. So let's go ahead and look at that derivative now. I'm going to mark it because we have a lot of functions running around. We have f of theta and now we have f prime of theta. So let's go ahead and make sure we mark this. So we have 1 plus sine theta, which is our bottom function, times the derivative of cosine. The derivative of cosine is negative sine, minus the top function times the derivative of the bottom function. Now the derivative of the bottom, I'm starting with a binomial here. The derivative of 1 is 0. The derivative of sine theta from up above is cosine theta. And you're going to want to have those 6 trig derivatives memorized because we're going to use them so often that if you don't have them memorized and you have to look them up every time, it really adds a lot of time and work to your problems that doesn't need to be there. And plus you'll have to have them memorized for the test anyway. So from here it looks like we can go ahead and simplify a little bit. So when we start simplifying this, the first thing to do is to take this negative sine theta and distribute it through to the 1 and to the sine theta. That gives me negative sine theta minus sine squared theta, and then of course negative cosine squared theta. It looks like we could not really combine anything here, but if you look at this piece right here, we should be able to factor out a negative 1. And when we factor out a negative 1, we'll be left with sine squared plus cosine squared, which of course is our nice Pythagorean identity. And we know that sine squared plus cosine squared equals 1. So I'm going to factor out that negative. So I'm left with sine squared theta plus cosine squared theta then, when that's factored out, all over 1 plus sine theta quantity squared. Okay, now, actually I have a mistake here. If I factored out that negative, this should be a positive. And now this piece right here, sine squared plus cosine squared, this equals 1. So in my numerator, I still have my f prime of theta. This is equal to negative sine theta minus 1 all over 1 plus sine theta quantity squared. Now if you wanted to, you could have plugged in the pi over 3 any point as soon as we took that derivative. So if you wanted to, you could have plugged in that pi over 3 clear up here. I think it's a little bit more difficult to plug in, but if you want to, you can. I'm simplifying before I plug it in, so it'll be easier to plug into. And also, if we were going to take a second derivative, we would want to simplify this first before we actually took the second derivative, because up here, if I took the second derivative of this, it would be awful. I'd have 2 product rules, I'd have a chain rule, which we don't even know about yet, and a quotient rule as well. So simplifying a lot of these does help. Looks like in the denominator I can factor out a negative. If I factor out a negative, I'm left with 1 plus sine theta, which looks familiar. In the denominator, I'm left with 1 plus sine theta quantity squared. And of course, now that I have this factored, I can do some canceling. This entire binomial will cancel with one of the binomials in the denominator. Okay, so when we rewrite then, I'm left with f prime of theta is equal to a negative 1. Don't forget that negative 1 that's in the numerator, all over 1 plus sine theta. Now what this is the slope of the tangent line at any point along the graph. And that's along the graph of, what was that? Was it cosine theta? Yep, cosine theta over 1 plus sine theta. Now, I'm not interested in the slope of the tangent line at any point along the graph. And of course, we'd have to watch out where this could be undefined right here. Okay, I'm interested in the slope of the tangent line at a specific point. So I want to look at f prime of pi over 3. So that means anywhere that I see a theta in this original derivative, I plug in pi over 3. So I have a negative 1 in the numerator. Now the sine of pi over 3, we already worked with that. That's square root of 3 over 2. I could find a common denominator here, and I'm left with 2 plus root 3 over 2. And that will flip. And when that flips, I get a negative 2 over 2 plus root 3. I'm going to rationalize from here because hopefully something will be a little bit nicer to work with. We'll see. And has a negative 2, 2 minus root 3. And in my denominator, I'm going to have 2 times 2 is 4. My outside and my inside terms cancel. That's why we multiply by the conjugate. And then my last terms, root 3 times root 3 is 3, and it's a negative 3. So it looks like f prime of pi over 3 is going to be equal to negative 4 plus 2 root 3. This is the slope of the tangent line at a specific point, pi over 3. So let's go ahead and kind of summarize again. We have a point, and our point was pi over 3, 2 minus root 3. And the slope of my tangent line I just found up here was negative 4 plus 2 root 3. So now I have all the information I need to go ahead and write the actual equation of the tangent line. To write the equation of this tangent line, then, I need to start looking at the generic form, or the general form, the point-slope form of the equation. So we start with y minus y1 is equal to m times x minus x1. Now for this one, x1 is your x-coordinate, y1 is your y-coordinate, and of course m is your slope. Now plugging in here is not going to be as obvious as it usually is, because I'm plugging in an entire binomial for my y1 value. So you need to make sure not only do you have your minus sign, but then you have parentheses so the negative gets distributed. M is my slope, and again we need parentheses here to indicate, this is my entire slope, to make sure it distributes through properly. And then I'm left with x minus pi over 3. And we want it in y equal mx plus b form. So let's go ahead and look at this. Y minus 2 plus the square root of 3 is equal to negative 4 plus 2 root 3x, minus pi over 3 times a negative 4 plus 2 root 3. And then of course we want to move all of this across. This entire value right here is my slope. So I don't want to distribute it through to that x, because that coefficient is my slope. And because that coefficient is my slope, I want to keep it grouped together. And then over here I have my minus pi over 3 times a negative 4 is a positive 4 pi over 3, minus pi over 3 times a positive 2 root 3 is going to be a negative 2 square roots of 3 pi over 3. I'm going to add the 2 across, and I'm going to subtract the root 3 across. It's not pretty, but this entire value right here is our y-intercept. See, so this is our slope, and now this is our y-intercept. And I could find a decimal approximation, but this is a great solution. The only thing I could think of that we could do here is to go ahead and find a common denominator. Not for the slope, of course, but for my y-intercept. So I have y equal my slope, negative 4 plus 2 root 3x, plus, and I'm just going to group all this together. My grouping symbols won't mean anything here because I don't have a negative out front to distribute, but I want to find that common denominator. So I have 4 pi minus 2 root 3 pi. Now for the 2, I want a common denominator of a 3, so I'm going to multiply top and bottom by 3. So I have plus 6/3, actually all of these are over 3's, minus 3 root 3 over 3, because here again I want to multiply top and bottom by 3. And then of course rewriting this with my answer, I have a negative 4 plus 2 root 3x plus, is there anything we can combine? The pi's could combine, but they're not integer values. The root 3 could combine, but the pi will throw it off, so I think we just need to go ahead and write it out. 4 pi minus 2 root 3 pi plus 6 minus 3 root 3 all over 3. And this is my y-intercept. So this is my equation of the tangent line to the graph of cosine theta over 1 plus sine theta at the point pi over 3. Now if we graphed our original function and the equation of our tangent line that we found by using our rules, it does look pretty reasonable that this could be the correct tangent line. Pi over 3, we could have renumbered this to be multiples of pi over 3, but pi over 3 will be somewhere between pi over 4 and pi over 2. Now pi over 3 would be somewhere right in here, it looks like. And it does look like this equation that I came up with, and this blue equation is this slope of my tangent line, or the equation of the tangent line, looks very reasonable. So it's always a good idea to plot these in Maple and have a look at not only the original function but the equation of the tangent line as well to see if it makes sense. Let's go ahead and look at one last example where we're looking at higher order derivatives. So if we start with the function f of x equals sine, I want to find the sixth derivative. Okay, so we want to go down and we want to determine what the sixth derivative is with respect to x. So we're going to start with f prime of x. The derivative of sine is cosine. F double prime, the second derivative, the derivative of cosine is a negative sine. The third derivative, the derivative of sine is cosine, but I have to drag that negative along. The fourth derivative, I drag along the negative. The derivative of the cosine is a negative sine. Minus a negative is the same as a positive sine. And if you notice, I'm right back where I started here. Now I'm going to take the derivative of sine to find my fifth derivative, and then I'll take the derivative of the cosine to find my sixth derivative. The derivative of the cosine is a negative sine. So going through and finding my six derivatives, I get down to the negative sine of x for my sixth derivative. So the important thing to remember here when I'm talking about derivatives of sines and cosines, I do have that pattern that is occurring here. It goes sine, cosine, sine, cosine, sine, cosine, sine, and then of course my sines go positive, positive, negative, negative, positive, positive, and it would go negative, negative as well. These patterns are important to see because in Calc 2 you'll be looking at these patterns in order to try and write an expression that basically would produce that type of a pattern. Now if we're looking at, I think I said that was the last example, but let's do one more, these are fun. Now if we're looking at something other than sine and cosine, these get pretty complicated. So for instance, let's go ahead and look at y equal, let's do tangent squared of x. Okay, well I want to find, well we'll just take some derivatives until we kind of run out of space here. So I want to find derivatives. Well the first thing to remember is this is actually tangent times tangent. And again, we don't know the chain rule yet, so I can't go ahead and use our little shortcut here. So I'm going to have to use the product rule. So here's my product rule. So y prime would be the first function times the derivative of tangent, which is secant squared, plus the second function times the derivative of this tangent, which is another secant squared. Now if I wanted to find a second derivative, I could certainly do that, but I don't want to find a second derivative without simplifying this a little bit first. If I rewrite this, I have 2 secant squared of x tangent of x. I don't know, we might not even go and find another derivative. If we were to find another derivative, I would write this out again. This would be secant of x, tangent of x. And then I could treat this as one of my factors. This is a second, and then within this factor I would have to have another product rule. Let's go ahead and do that. It looks like it would be a good one. So I'd have my first function times the derivative of the second function plus the second function times the derivative of my first function. Oh, and I forgot my derivative notation here, so I better stick that in there. Now it's the derivative of this piece that's going to be another product rule. Now again, we don't know the quotient, or sorry, the chain rule yet, so we can't use that. So secant x. The derivative of tangent is secant squared. So for this first one, it looks like it simplifies to 2 secant to the fourth. Now, the derivative of this piece is going to be a product rule. It's going to be kind of long. We'll see if we can fit it in here. So here's the tangent that I'm dragging along from here. I'm going to pull that 2 out front right here as well. Now I need the derivative of secant times secant. So the derivative of secant times secant, I'll have the first secant times the derivative of the second secant. The derivative of secant is secant tangent. And then I'll have the second secant times the derivative of the first secant. The derivative of secant is secant tangent. And again, you have to have these trig derivatives memorized because we're going to be using them so often. And kind of a big mess here. Let's go ahead and simplify this up. Was this y prime or y double prime? This is a rewrite of y prime. This is y double prime. Yeah, y double prime. So I'm left with 2 secant to the 4th of x plus, okay, let's see what we have here, 2 tan x. Now, this is going to be secant squared tangent. This is going to be secant squared tangent. So I'm going to have 2 secant squared tangents. Then I can take these 2's and combine them. Secant to the 4th, 4. Okay, now we have a 4. I'm going to have a tangent times a tangent, which is tangent squared of x, secant squared of x. So that's one simplification that we could have. We could factor out a secant squared here, but if I did, I'd be left with secant squared times 2 secant squared plus 4 tangent squared. I don't really see an identity that would really work with that, so I think this is great for our second derivative. Now, third derivative, we can see this is getting pretty out of control, and so that's why in our next lecture we'll be looking at the chain rule, where the chain rule would make this derivative, this third derivative, easier, but it's still going to be pretty ugly. So what do you guys need to do? You need to memorize your 6 trig derivatives. And you need to be able to use them on the quiz on Tuesday when you come back to class, and you have to have them memorized. You won't have notes for that. So let's go ahead and review them one more time. The derivative with respect to x of the sine, the derivative with respect to x of the tangent, the derivative with respect to x of secant. Now, I'm splitting these up into 2 directions for a particular reason. First of all, I have all sine, tangents, and secants over here, and then over here I'm going to put my cosine, my cotangent, and my cosecant. So notice on this side, these all start with C. Now if you notice also from the original that I printed out from the textbook in the very beginning of this lecture, the derivative of any function, any trig function that starts with the letter C, derivative of cosine, cotangent, cosecant, are all negative. So these are all negatives. On this side, the derivative of anything else that doesn't start with the C, these are all positive. And that's just one way that I try and kind of remember what's going on here. The derivative of sine is cosine of x. Remember, the argument does not change. The derivative of tangent is secant squared of x. The derivative of secant x is secant of x tangent of x. Now, I would encourage you to always write both arguments. A lot of times people just write the letters S-E-C-T-A-N, secant tan, but that doesn't really work here. We need secant of x, tangent of x. We need this argument because pretty soon that argument's going to be changing. It's not just going to be a nice little monomial term. Now, over here on this side, the derivative of the cotangent is going to be, the derivative of cosine is going to be a negative sine. The derivative of cotangent is negative cosecant squared of x. The derivative of cosecant x is negative cosecant of x, cotangent of x. And again, you must have this memorized as soon as possible. On your quiz on Tuesday, you're not going to have a set of notes to go from on this one, so you need to have these memorized. Good luck!